Well, greetings, everyone. This session is called Optimization of Green Ammonia Projects Using Universal Classes in Plexus. First, before I start, I would like to thank the organizers for this great opportunity to present here today. My name is Jovana Nikodijevic, and I am a power system consultant at Go2Power consulting company with headquarters in Belgrade, Serbia. We aspire to become the leading consulting company amongst other small businesses in our area of expertise. We have vast experience in transmission and grid studies, employing leading software tools to anticipate and solve network issues. We focus on delivering extensive power system analysis, including integration of renewable energy sources, generation optimization, and transmission expansion planning over any time frame, all supported by thorough market analysis. Using Plexus, we aim to create the most adequate solutions for custom models of power system utilities and transmission system operators, implementation objectives and technical requirements, and also preparing templates for integration into the Plexus database. We also employ other tools such as PSSC, SYNCL, ETEP, and PSCAD for comprehensive network studies to ensure robust design and operation of power systems, including substations, cables, and overhead lines. Recently, we have been increasingly involved in feasibility studies for utility-scale green ammonia and green hydrogen projects. It's important to recognize the widespread application of hydrogen across various industries, such as agriculture, shipping, mining, transport, chemical industry, and so on. However, a critical challenge remains. Currently, 99% of hydrogen is produced using fossil fuels. Furthermore, hydrogen is also used to produce ammonia. Traditional ammonia production is one of the largest industrial contributors to global CO2 emissions due to its reliance on fossil fuels. Green ammonia, on the other hand, stands for ammonia that is produced through processes that are entirely renewable and carbon-free. Benefits of green ammonia extend even beyond just its production. So as an energy energy storage medium, ammonia can be easily stored at modest pressures or refrigerated conditions, making it the perfect candidate for the improving of availability of renewable energy sources. Also, it can be burned in engines or used in fuel cells, producing only water and nitrogen as byproducts, elements that have no warming effect on our climate. As it is overall easier and cheaper to store and transport than hydrogen, as a hydrogen carrier, ammonia can be a practical solution to challenges associated with hydrogen. Looking ahead, the role of green ammonia projects is set to be crucial in our journey towards net zero emissions by 2050. Its application in sectors such as sustainable agriculture, marine transport, and renewable energy storage is a necessity and represents an essential step towards our greener future. The key concept in our modeling of green ammonia projects is universal class, a building block for creation of any model of any system that is subject to time sequential constrained optimization. Using Plexus universal class, we can capture the properties of systems that are traditionally modeled with specialized classes, but also we can capture the properties of the systems that specialized classes are unable to effectively represent. So using classless universal classes, we are able to model the whole production chain of green ammonia projects. So from renewable energy to hydrogen, from hydrogen to ammonia, as well as hydrogen and ammonia storages and battery energy storage systems and other derivatives if applicable. Okay, so we are using universal classes to represent objects of the green ammonia system, their memberships and properties. The commodity class is used to represent chemical substances and electrical energy. Production of the commodities is described by the process used by the facility to produce the respective commodity and other secondary commodities. Flow nodes are used to encapsulate the physical locations of the facilities. If we want to address the efficiency and losses of transportation of commodities through pipelines or similar physical flows, we can use flow paths between flow nodes. Flow networks define boundaries or areas where the respective commodity circulates or flows. We have flow storages that represent locational storages of the commodities in a flow network. And finally, finally, we have market class that can represent the actual demand which could drive the whole production process. Based on our clients' needs and technical requirements, we can define different scenarios to optimize the amount of facilities needed to fulfill the ammonia demand in the long run. For example, we can estimate the required capacity of PV or wind power plants or the size of ammonia and hydrogen storages and so on. Additionally, we can define, we can adjust the outputs. We can adjust the output given any realistic constraints. So, for example, we can define maximum units built in 1 or more years and so on. I'm sorry, I'm a little bit nervous. Okay. We can define different optimization scenarios based on the technology used by different manufacturers of the facilities. So, for example, we can provide different power curves for different ammonia plants and so on. Additionally, we can define different battery energy storage system objects that vary in capacity and duration to determine whether there is a need to use them, and if so, which technology should be preferred. We can also include short-term dispatch by providing time characteristics of solar and wind power plants. For solar and wind potential at the project site, as well as any energy market-related properties and constraints. We can also define degradation of different plant efficiencies or battery energy storage systems. Based on our experience in feasibility studies for green ammonia projects, we have pinpointed several key optimization drivers. So firstly, the size of hydrogen and ammonia storages are significantly, I don't know why this is happening. I didn't click anything. Sorry. So the size of hydrogen and ammonia storages significantly depends of frequency of offtake and volume extracted. Additionally, the size is contingent upon the availability of renewable energy sources. As facilities that operate on low capacity factors are less efficient, that in turn increases the levelized cost of production. So also, although technically feasible, the cycling of facilities is generally avoided to maintain the system integrity and the system efficiency. If there is the access to the grid, we can mitigate the need for battery energy storage systems, as well as avoid wastage of excess energy. Well, moreover, we can monetize the surplus of electric energy. And finally, if we take into account the degradation of battery energy storage systems and different plant efficiencies, we can avoid the potential oversights or any inaccuracies in our optimization. So using universal class, we have a vast, we can model a vast majority of the systems. We have a means to define the properties of different systems, of different objects in such systems, and universal classes are the perfect tool for such optimization. Well, I was maybe too fast, but okay. Thank you all for your attention and for joining today's session. If you have any questions or you want to share your thoughts or insights, you're welcome to. Yeah, thanks.
Lovely, thank you very much. I certainly learnt quite a lot from that. Do we have any questions? Okay, if you wait for the mic. Thank you.
Yeah, thank you for the presentation.
Thanks.
It's unfortunately not a modelling question, but more along the lines of ammonia and acceptance of it. I'm just interested, was only positives at the start? I'm wondering, are any of your people who are looking at it expressing reservations about nitrogen cycle? So similar issues to the carbon cycle, there are issues with the nitrogen cycle. So I'm just wondering if people express any reservations about using ammonia and increasing the amount of nitrogen.
Well, I'm not familiar with such questions for now. I know the ammonia projects are now excessively in feasibility parts of the studies, so I don't think the cycling of that type is the problem right now. But
other questions? Oh, we have another one.
I have a simple one. Why did you choose the universal class over electrical plus gas? Well,
a universal class gives us the opportunity to model any commodity in any system. Well, on the other hand, electricity class can model only electricity. Well, we can certainly model something like this in traditional classes, but I think it would be very complicated and more complicated than using universal classes. So it's like, as I said, the building block for other classes. So we can represent any model that was earlier represented with electricity classes, water or gas classes, and so on. We can represent them using universal classes.
I think we have some examples of green ammonia in the lab using the gas class. I think there's probably pros and cons of both, or you can mix and match between them.
Yeah, definitely. We can merge universal class with all other classes also.
Okay, another question?
Thank you very much for the presentation. My question is about the ammonia synthesis process, the Haber-Bosch, because this is more complex than the electrolysis. the balance of plant, the BOP, are you modeling it separately, or you're just taking, for example, one facility as the ammonia plant synthesis, and then you go straight to the market class?
It depends on technical requirements and our clients' expectations, but we have modeled ammonia plants, for example, when we model the complicated power curve by using 2 power plants instead of 1, or by using 1 auxiliary plant to represent the constant part of the, like no load usage of energy.
And a follow-up question is, what about the heat cycle of the Haber-Bosch? Are you also using perhaps the commodity class to model the heat coming out of the Haber-Bosch, for example, for some residual, let's say, uses?
Yes, we can also use universal classes to define any properties of heat flow part.
Thank you, thank you.
Okay, any other questions? We have one at the front. They're trying to make you walk us up and down as much as possible, I think.
With ammonia being more shippable than hydrogen, what was the scope of your study? Like, did you consider, say, the globe as a whole market, or were you just looking at a single area?
For now, we have one project that is in feed stage of the project, and we have one commissioned project, but they are, I would say, about 25 megawatts or so. So we are not currently involved in such big scale projects, I would say, but maybe in the future. If that answers your question, I'm sorry.
We do have time for any other question, or is a decision between another question or going for a slightly early tea break, which is quite... Okay, I think we're voting for a tea break. Well, we have a tea break and we all need to be back, well, either in here or in the other room. We're restarting again at 4:30. So thank you for your attention and great questions. We'll see you shortly.
Thank you.